Hey everybody, just wanted to go over the review for your first exam. And I decided not to write everything out, but I was just going to talk you through some of these answers. So I think we'll just go through this. We've got Chapter 1 review, students gathering information about students at her college for a statistics project. She asked students in each of her classes how they feel about the federal government forcing insurers to provide birth control to all women they insure. 85% of the students she asked feel this is appropriate. So the population, because she's talking about students at her college, the population is students at her college. But of course, the sample is just the students selected for the survey. She was asking yes/no questions about whether they think it's, how they feel, and students are saying it's appropriate. That's a yes/no question. So yes/no responses are categorical. Remember, there's two types of variables or data. They are either categorical or quantitative. This is yes/no, definitely categorical. In what parameter is she interested? She wants a percent from a whole population. Any I don't want to say statistic, any measure of an entire population is called a parameter. But she couldn't get the parameter apparently because she only asked students from her classes. She did a statistic, and that was the 85% that she observed in her data. She did a convenience class because she only worked with students that were sort of convenient to her. Those were her classes. And convenience samples always will include selection bias. And selection bias is just one of these things where some people are more likely to be selected than others. And so that's a selection bias. All right, so selection bias is anytime you have a sample where some people are more likely to be picked than others, that's selection bias. And so that's what's happening here. The study's observational, not an experiment. There's no treatment or anything. She's just getting information from people. Would it be appropriate to use this study to make inferences about the population? And of course, no, the data would be biased in the way she did this. Okay, going to the second question. In a recent study, researchers randomly gathered a collection of volunteers to put them into two groups based on whether or not they drink diet soda. One group consisted of people who drink a can of diet soda each day. The other group consisted of people who don't drink diet soda. Each member was weighed, and they were weighed again 1 month later. The non-diet soda drinkers had no change in weight. Diet soda drinkers gained 1 pound each on average. Okay, so is it experimental or observational? I said the reason why it's observational is because there's no random assignment into groups. They were not, the groups weren't manipulated, which means there was no treatment given to one group. The explanatory variable here is whether or not they drank diet soda, and we didn't manipulate that variable. The explanatory variable again is whether or not they drink diet soda. That's a yes/no question, which is categorical. The response variable was just a matter of how much weight they gained, and that's a quantitative variable. Confounding variables are difficult. So here it says diet soda drinkers may already be struggling with their weight. And so this will always happen when you have groups that sort of just form naturally, and people aren't put into their groups by random assignment. So when you don't do random assignment into groups and people sort of just pick their group, that's because they have certain properties in common. And but one, of course, in this case would be that people are diet soda drinkers, and they're put into that group because of it. But they also might be struggling with their weight, and that's why they drink diet soda. So if they're struggling with their weight, it's not really maybe a surprise that they gained a little bit of weight. That would be a confounding variable probably. So it says, was a placebo implemented? No, there was not a placebo, but it's not an experiment, so we don't do. I mean, we could have given them a placebo, but it's not an experiment, so it's not really something that makes any sense here. Now, which was the control group? Well, again, it's not an experiment. If it was an experiment, it would be the people who don't drink diet soda. Treatment group would have been the people who do drink diet soda, but again, it's not an experiment. Would it be appropriate to conclude that diet soda causes members to gain weight? I think no. Cause and effect can't be concluded in an observational study, and you have to do a proper experiment for that. So just because these variables did correlate, that the diet soda drinkers did seem to gain a little weight, it doesn't. There's no way to determine the cause from this study for the weight gain. Just because of these confounding variables, we have alternate explanations for the weight gain. Okay, so is the sampling method likely to create bias? I think we kind of talked about this. It's a sample of volunteers. It's also a convenience sample, so definitely you'll have selection bias. I already talked about that. Okay, now there's another problem here. The ABC Darien project. Inner city children 3 years of age were randomly selected. Their parents were all from the same socioeconomic background. Each child was randomly assigned to one of two groups. So that you see that random assignment into two groups, that's one of the things we look for in an experiment. In one group, children were provided with high quality preschool education. In the other group, children were received child care without any preschool learning. Children in both groups were provided with healthy food supplements. I think that was just to make sure they're all getting, trying to eliminate differences in diet as a confounding variable, I guess. Students were followed for years and many differences were noted. This is a real study, by the way. Among these, it was found that the children who had quality preschool were 4 times more likely to graduate from a 4-year college. So that says a lot. Is the study experimental or observational? It is an experiment. There was random assignment of individuals into the groups, and then the explanatory variable was manipulated. That explanatory variable would have been whether or not they had quality preschool education. So yeah, the explanatory variable, high quality preschool, yes or no, definitely categorical. The response variable, here it was measured that people were graduating from 4-year colleges. Once again, that's a yes-no question, so categorical. Blinding, I don't think you could introduce blinding. That's where you give a treatment, but people don't know whether it's the real thing or a placebo. Of course, you can't have a placebo for whether your kid or not, your kids in preschool, they would know. Other confounding variables, nothing obvious. The kids are put into the groups randomly. I don't, you might be able to come up with some ideas, but I don't think there's anything obvious here or clear. So I would just say no. The control group would be the kids that didn't have the treatment, which was the preschool, and the treatment group, of course, were the kids with the preschool. Now, would it be appropriate to conclude that quality preschool causes children to be more likely to graduate? The answer is yes. It is appropriate because the experiment was controlled pretty well by having 2 different groups created by random assignment, and we had different treatments applied to those groups. Okay, so that's the chapter 1 review. Most of that will be in a multiple choice form. Okay, now for the chapter 2 questions, I just had nothing much more complicated than giving you this data set. And the first thing I wanted to do was have you do a class table. So you have to do the range. The range is the max minus min, 4 minus 9.4, sorry, 0.94, my bad. And whatever that is needed to be divided by 5, and that comes out to 0.612. We're going to round it to 2 places and make it bigger because all of these have 2 places, and we always make the class width bigger. Okay, we start at the min, which is 0.94 here. And then we're adding the class width, 0.62, as we go down the table here. Okay, the second lower limit is 1.56. So the first upper limit needs to be 100th below that 1.55. So 55 is right below 56 here. And that's kind of the logic. And then we just keep doing that. 217 is right below 218, at least as far as the nearest 100th is concerned, and so on. As we go down the table, in either side of this, we're adding the class width. Okay, same thing on this side. Okay, just keep adding the class width to get all those values. Okay, and this is a frequency table, and I did make a note that I could ask for relative frequencies on the exam, but I haven't, I don't know which one. Okay, so the class boundaries is a reminder, you can just take all these upper limits and add 5s after them, and that'll give you all the class boundaries except for the first one. So 1.55, just change it to 1.555. 2.17 changed to 2.175, and so on. And then from one to the next, we're adding the class width here. So you just keep doing that. And then the first class boundary, you would subtract the class width to get to that. And that gives you all these values down here on the number line. And then, of course, the frequencies are from the tally here. So that's pretty straightforward. I could do relative frequencies here, but I'm not too fussed either way. It could be either one. Okay, then I asked you to skip the box plot in question 5 and do that last in chapter 2. So it says in question 6 here to describe center, shape, and spread. So for the center, you could just give the median, and I do the median down here, 2.83. So that's one way of describing the center, or you could use the mean. It doesn't really matter what you do here. You could use the mean here of 2.809, or you could just kind of guess it. It's around 2.8, obviously. So you can see from the graph too, the average is going to be up in here somewhere. Okay, so not worrying about too much precision with the center. The shape is a clear skew left. You can see it's kind of trails off on the left side. And of course, once you look at the box plot, you can see it's clearly skewed to the left. It's longer on the left side. So that's shape. Spread, I just give the standard deviation. So the standard deviation is down here, so I just gave that as a measure of spread. That's why we have standard deviation. Okay, notice we're rounding the standard deviation down here to 3 places because the data had 2 places. Okay, just add one, make sure you have one more digit to whatever, one more digit more than what's given in the problem. Same thing with, so that's the standard deviation, but same thing with the mean. Those get 3 places. Here's the 5-point summary up here. I'll refer to that in a bit. Then the usual range here, you just take the mean, subtract 2 standard deviations, and the mean plus 2 standard deviations, so like that. And so the lower limits, and then you can decide if a value is unusual. Apparently the 0.94 in the data set is the min here, and that's the only one that's outside of the usual range. The lower limit of the usual range here is 1.1, and you've got this 0.94 value, so it's definitely outside of the range. The next value is 1.69, and that's definitely in the usual range. Okay, so we just have the one value outside the usual range. It turns out that it's not an outlier, but it is unusual. Okay, now taking the z-score of 0.94, here's the formula for the z-score. You would put the 0.94 in for x, and then X bar is up here, and of course the standard deviation down here. So you just plug all that in, and we get negative 2.19, and this is unusually low because it's more than 2 standard deviations below the mean. Okay, now percentiles, you have to count. This is a percentile for 3.80, so you actually have to go back and count how many values are less than 3.80, and it's all of these. Okay, so how many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 values out of 19, I think. So you can see me with the percentile doing 16 out of 19, and then multiply by 100. It's 84.2, which you would round to a whole number. It's the 84th percentile. Percentiles get rounded to whole numbers. All right, now the median, I just recommend you get that from your calculator. The mode is the most frequent value. Mid-range, the min plus the max over 2. So here they are, 2.47. The range is the max minus the min. Now let's go ahead and get to that 5-point summary. Again, the calculator is going to give the min, the first quartile, the median, the third quartile, and the max. Just a reminder, after you sort the data set, the median is the central value. The first quartile is the central value of all the values below the middle. And the third quartile is the median of all the values above the middle. And the interquartile range is Q3 minus Q1. Q3 is here, Q1 is there. Just subtract those to get the interquartile range. And then we do the fences. The lower fence is the first quartile minus 1.5 times the interquartile range. So the first quartile, 2.14 here, minus 1.5 here, times the interquartile range here. Okay, and then for the upper fence, you start at the third quartile here, and you add the same. You add 1.5 times the interquartile range. Again, that's 1.48. Okay, and you get these two values, and anything outside of those values would be considered outliers. This one's negative, and there's nothing negative in the data set, so nothing below this, and there was nothing above 5.84, I don't think. The highest value here was 4. So there's definitely no outliers. Oops. And I think we can go past that. And then we can take a moment and look at that the box plot. It goes from the min as at the tip of the first whisker up to the first quartile. Then we draw the box up to the third quartile here. And the median is where the line goes through the box. And then from the edge of the box, we go to the max. Now, I want to be real careful because it is possible that there is an outlier. So if the min had been an outlier, then that whisker does not go up to that. You would go up to the lowest non-outlier. Whatever that is, that's where the whisker goes to. So you do something like that. And same thing on the other side. If the max was an outlier, you would not draw the whisker up to the max. You just go to the highest value that's not an outlier. Okay, so just you could refer to your notes to look at an example that we did of that. I think that pretty much covers everything there. Now, just take a moment to go through problem 17, which will be worth a bunch of points because there's so much to it. So I'll give you a table sort of similar to this. I'll just, first thing you should do is total up each row and then total up the two columns this way. And you'll get numbers that add up to whatever your sample size is in either direction. So 48 and 52 is 100, and all of these row totals add up to 100 as well. Okay, and then most of the problems you're just going to count how many times something happens and divide by 100. Unless we put a condition on something, in a conditional probability. So we'll talk about that in a sec. So here, the first question, probability of female, you just count how many females. There were 48 out of 100, and so there's your answer. Okay. Probability of male, you just want to count how many males. 52 out of 100, and there's your answer. Okay, you do not need to reduce these fractions or go to decimal or anything. Now, F and B, that's female and B grade. Here, there's 22 out of 100, and there's the answer. Okay. M and B, that's male and a B grade, 18 out of 100, right there. Okay. Now, A and B, anyone that got an A grade and a B grade, those do not intersect. Those are mutually exclusive. So there's no way that you can get an A grade and a B grade in that class in one semester. So obviously the probability is 0 on that. Now, when we do F or B, you're counting all the females or males with a B letter grade. So you count all the females, there's 48 of them, plus 18 males that got a B. And so 48 and 18 would be 66, I think. So you just add this all up and you get 66 out of the 100. Okay, so that's how you do the OR problem. Just add up what you see. Now, these two are conditional. The probability of B given female. If it's given that it's a female, then you only look at the females. Okay, so given that it's a female, what's the probability of getting a B? Well, it would be 22 out of 48. That condition, it is given that it's a female here. And if it's given female, you only look at the females. It will reduce the denominator. Okay, so here we're talking about 22 out of 48, which you see. Okay, now probability of getting a B given it's a male, now you're only looking at the males. There were 18 males out of 52 people, so that's the probability. Okay, no fancy computations, you just got to know what it means. Now, this is the probability of B complement. That's for the rule of complements. You just do 1 minus the probability of B. And the probability of B is 40. There are 40 B's out of 100. And we're doing B complement. So you do 1 minus 40 out of 100. And if you do that on your calculator, you get 60%. So you can write that as 0.60 or 60%, however you want to write it. It's all good. Okay, now question 18, it says our class has 21 females and 12 males. And here I'm figuring out that that's actually 33 people altogether. You're picking 3 people randomly without replacement, and what's the chance that they're all female? Well, without replacement, initially there's 21 females. Then you pick another person, there's only 20 females left. Okay, and then you pick another person, there's only 19 females left out of, starting with 33 on the first one, then only 32 on the second, and only 31 on the third, and you multiply that all out, and you get this messy number, which will round to 0.244. Okay, and that is basically it. So I would just leave it at that, and best of luck to you all on the exam.